Okay, so our next set of notes is basically how we're going to start a chi-square GOF test, and that is chi-square, by the way. That's how I write it, so you'll know. It's like an X with a little curvy bar. And remember that GOF stands for goodness of fit. Okay, so the next part that we're going to talk about is how we write the null and the alternative hypothesis for a goodness of fit test. And there's a very specific way that the null and the alternative hypothesis need to be written. Okay, so when we're talking about a goodness of fit test, remember from yesterday that a goodness of fit is basically checking how a population that you would divide into groups by some characteristic, right, would fit a given distribution that you're told about. Okay, so the null, is always no difference, right? That there's no difference between what we're told and what actually is. So you have a couple of choices on how you can write this, depending on how many groups your population has been divided into. You could actually list out each one and its proportion. So you could either, list out groups with proportions. And we're going to do a couple of practices with these. Or, here's the thing, you could list out in words. So there's a couple of choices. Now, please keep in mind, since these are proportions, that the variable that you're going to use is always going to be p. And it's going to be p of whatever. So like if you were doing M&Ms, you would do like p of blue, and you would tell me the proportion of, what the distribution actually says it is. And you would do p of green and p of yellow, and, you would list all 6 colors out if we were doing M&Ms. Okay? The other choice is to write it out in words. And it's very specific as far as how it's stated, but it's not bad. It is literally that the distribution of, and you fill it in with whatever it is you're talking about. If it's M&Ms, you would say the distribution of M&Ms. If it's people, then you would say the distribution of people. Whatever it is, whatever your population is that's been divided, the distribution of blank is, and normally you would just put as stated, because it's normally stated in the context of the problem. Okay, or you would say that you could also say is correct, and then you would literally, that's all you would have to put, that it's just it's correct, that there's nothing wrong with it, because the null is basically that there is, again, no difference between what you're told and what actually is. Okay, that's always what your null is supposed to be. So again, the distribution of blank is as stated, and like I said, it's normally stated in the problem, or you could say it's correct. Now, here's where it gets interesting. The alternative, you're not allowed to say that the distribution is incorrect, or the distribution of blank is not as stated, okay? Because that implies that there's something wrong with every single group within that distribution, okay? Now, remember that you're taking a population and you're dividing it into groups, okay? So we're not allowed to say that they're all wrong, right? Which would be saying the distribution is incorrect. We're also not allowed to state that a specific proportion within the group or within the population is wrong, because we're not testing for any specific one group. We're testing that all of them are actually working. And again, I know that seems really weird, but we're not allowed to say it's incorrect because that means that all of them are wrong. So this is the way we state the alternative. At least one of the proportions is, is incorrect. Okay, That allows it to be, 1 all the way up to all of them, but we're not allowed to say that the whole thing is just incorrect. Okay? Even if you list out the groups like, P of green, P of blue, like you were doing M&Ms, your alternative would still be at least one of the given proportions is incorrect. Okay, you can actually say given on that as well. Okay, but that is how we actually state our null and alternative. You don't have to use a single variable. You don't have to use any kind of notation like mu or p if you don't want to. You can just write it out in words. And this actually works really nicely for the GOF test and the other 2 chi-square tests that we're going to be doing. It's much, much easier if we just write it out in words. Okay? So that's how the null and the alternative are written. So now let's talk about the conditions, because these are the 2 things that you're going to work on today, is basically the state and the plan. Okay, so what conditions should be met? The neat part is it's still random independent normal, but normal is the only thing that gets changed this time. We're still looking for either random selection, okay, and I haven't seen a whole lot of chi-square that happen to be like experiments, not for GOF and not for the other tests either. So you're probably not going to have random assignment. It's going to be some kind of random selection. And I'll keep looking to see if I can find one just to show you that, for the example. Okay, independent is still the rule. Your sample, times 10 is less than the population. Okay, you have to make sure that there's, at least 10 times your sample in your population. That actually should say less than the population, shouldn't it? So is less than the population. Okay. So that hasn't changed, and we still have to actually, write those 2 out. Okay, the normal one is a little bit different, because you're not looking at, most of the time you're not looking at just like 2 proportions where you could do what we did in the last chapter and state, that all of your successes and your failures are all greater than 10. Okay, so instead, because, you could be looking at several different groups out of one population, it's all expected counts, and not your observed, but your actual expected counts, are greater than or equal to 5. Okay, and we'd have the same thing, that same little twist that we do if somehow one of your expected counts was less than 5 when you were doing your math. You would say proceed with caution. Okay. So, but those are the actual conditions. So it's still random independent normal. This is what causes your chi-square distribution, which is really, really skewed. We talked about that yesterday. This is what causes the distribution to become more normal if all the expected counts are greater than or equal to 5. Okay, it's basically it's like a large sample type statement. This is sort of like the same thing as making sure your successes and failures are greater than 10 to make sure that your data is workable. The thing is, on this one, you don't have to say approximately normal afterwards. You just have to show or prove somehow that all of your expected counts are greater than or equal to 5. And that's part of what we do anyway, is calculating the expected value, because we need both of them anyway for to actually run the test. So you're going to calculate them anyway, and it's very easy just to write them out. Okay, so let's do a couple of examples here and see if that makes more sense when we look at it. Okay, where did my... that's weird. Where did my thing go? That's very strange. I have it copied and pasted right here. Delete. Okay, how about edit, undo, delete. Very strange. All right, let's check the properties. Well, that's weird, and you can see them right there. All right, well, give me a minute. I'll pull them up from the other one, since it's, being silly. All right, I don't know why it's not coming up. Come on. Just go to here. It's fine. I just copied and pasted it from the other one. All right, so let's take a look. That one. Why it didn't come up? Okay, so we're going to basically do our state and plan for the two examples that I have. Okay, so let's see what important information we have. Okay, our births evenly distributed. So they've told us right now what our distribution is. They expect them to be evenly distributed across the days of the week. Okay, so very important. And they've given us our sample size, which means we can then calculate our expected values, right? And we've been given our observed values. Okay, so we're going to write our null and our alternative hypothesis. So again, you could state in, proportion, and it would be, if you did it in symbols, it would be the portion of Monday. Well, if it's evenly distributed across the days of the week, would equal 1/7, and the probability of Tuesday would equal 1/7, and you would keep going all the way to the probability, or the portion on Sunday, rather, not probability, is 1/7. So that's if you're going to do that in symbols. If you're going to do this in words, then it would be that the distribution is as stated. Births evenly distributed throughout the week. Okay, and that's basically referring back to what it says in the statement. You're basically regurgitating it back to them, which is what we normally do. So the distribution is as stated, births evenly distributed throughout the week. Okay, so here's the ha. Now remember, we say at least one. Okay, so at least one what? Well, what are we talking about? We're talking about the days of the week. So at least one day is not, we could say evenly distributed, we could say equal to the rest, equal in births to the rest of the week. Because basically what they're saying is that, if you have 14 births, then there would be 2 on Sunday and 2 on Monday and 2 on Wednesday. They're equally distributed, okay? So the distribution is as stated as our null, but there's no difference. Births are evenly distributed throughout the week. At least one day is not equal in births to the rest of the week would be our alternative. All right, so let's go ahead and do our conditions, okay? Random. You go back into your statement always like normal. Random sample given, so we're good. Or sample was randomly taken. I've seen several of you write, and I like the way that sounds. Okay. Independent. There are, same thing as we've always done, more than, well, they took a sample of 140 times 10. Well, 140 times 10 what? Okay, so in a large city. So there are more than 140 times 10 births in a large city. Okay, and it's not like they actually counted up 1 week. They literally just counted up 140 births from a large city and stated what day they were in. All right, so your normal condition. Now this is where we have to go back and actually do our expected counts, okay? Now remember, these are your observed, all right? Well, if what they're saying is true, if the births are evenly distributed throughout the week, and they're looking at 140 birth records, how many should be on each day of the week? Each of them should be 20. Okay, so all you have to state, because you've already gone and actually calculated them and written them somewhere on your paper, right? If they give you a chart, write the expected counts next to the observed ones, and then all you have to do, all expected counts are greater than 5, and that's it. That's what you're doing today, is you're doing the state and the plan. Okay, one little thing for you to think about before tomorrow, because that's when we're going to start actually doing the test. If you're expecting to get 20 every day, which one of these observed counts, or more than one, would be the most surprising? Okay, would it be surprising to get 18 when you're expecting 20, or would it be different or really strange to get 27 when you're expecting 20? Okay, which ones of these would have the biggest difference? And that kind of answers the question if you've looked at page 679, no, sorry, 681, on why we divide by the expected value, because we're trying to see proportionally which one has the biggest difference from the expecteds. But that's what you're doing today, is you are doing state and plan. Let's do one more example, and then I'll let you start on your work. Okay, I'll give you a minute to read and think about, the important information that we have here. Okay, so we're going to have to do some work to figure out what the proportion should be and to figure out what your expected counts should be. Okay, and we're going to use the Punnett square to find the expected values in our proportions. Now, again, I know it's probably been a while for y'all, taking biology, but if it's big G, little g, and you're crossing them, big G, little g, with big G being, I believe, green and little g being the recessive yellow, okay, if you cross them, then you end up with GG, which is green. Okay, you have big G, little g, big G, little g, and then little g, which is yellow, and big G, little g, which is, I think they called it yellow-green. All right, so knowing how the Punnett square works, if you're crossing these two plants, then the proportions, right, that you should get based on, you have 4 squares here, you should have 25% of the plants should come out green, 25% of the plants should come out yellow, and 50%, since there's 2 of them, should come out yellow-green. Okay, that's going to be how you would show your work for your null when you're stating that the distribution is as stated, and then you would say 25% green, 25% yellow, 50% yellow-green. Again, you could also do it in symbols, where you would do the proportion of green is, 25%, proportion of yellow-green, and you would, write it out that way. Or, since you've already shown the Punnett square, and this would be something you'd be expected to do on your open response question, you would say the distribution of plants is as shown, 25% green, 50% yellow green, and I'm running out of room. Yellow green, 25% yellow. All right, so that's your null. And your alternative in this case, remember the same words, at least one proportion is not as shown or is not correct. You just can't say that the distribution is not correct. You have to say at least one proportion is not as shown or is not correct. Okay, so our conditions, again, random, independent, normal. Random in this case, and I guess this would be kind of considered a experiment, but we still get to go with randomly selected. Okay, independent. There are more, and this is where we go back to the, sample size. Our sample was 84 pairs. 84 times 10 tobacco plants. Right? Okay, and then normal. So we need to go up and we need to figure out what our expected counts are going to be. Because we have our observed. These are observed counts. Okay? Now, this is where we have to do a little bit of math for our expected values. I have 84 pairs. Okay? So 84 pairs. I'm just going to get a little bit of room here. Okay, so 84 pairs. 25% should be green. How much is that? Well, that's 25% of 84. Okay, 50% should be yellow-green. Well, 50% of 84 is 42. And 25% should be yellow. And this is going to happen more often than not, where you're going to have to do some kind of work. Usually it's going to be multiplying like a proportion times the total to show your expected counts. Okay, to show your actual expecteds that you need in order to be able to run this test. And all of our expected values or expected counts are greater than 5. And we've shown it. And this is what I'm going to expect you to do with the problems that I'm going to give you tonight. I think it's a total of like 4 problems. But this is what I expect you to do. You're going to do your state. You're going to do your plan with your conditions. And then you're going to make sure that you show how you're getting your expected counts. Okay? And that is it for today. Tomorrow we'll actually run a test on these same problems. And you should already have the notes for today, so if you've got enough room on your notes, just go ahead and leave the room there, because tomorrow we'll go ahead and finish up with do and possibly conclude. All right, so your assignment is in section 11.1. That is on page 692. Okay. And I want you to pay attention very carefully. 1, 2, 5A only, and 6A only, because that's just talking about your expected counts. Okay, it's basically like doing your conditions. The rest of it is literally make your hypotheses. Okay, and that's it. So this is pretty much hypotheses and expected counts. This is pretty much conditions. And it's about actually the same problem, because I think 1 and 5 go together and 2 and 6 go together. So, all right, have a good afternoon. I will talk to y'all later.